Hello everyone, I'm Paolo Marzioli.
And I'm Lorenzo Frezza.
And welcome to the third video tutorial for the SDR Play course on understanding radio communications using SDRs. In this video tutorial and in this lecture, we show the second part of the practical exercise, which is aimed at setting up a GNU Radio companion data processing environment for receiving data through your RSP radio receiver. I immediately hand over to Lorenzo that will show through his computer screen how to continue the exercise and how to complete it by receiving data through the SDR Play RSP. Let's get started.
Thank you, Paolo. Today we'll continue playing with GNU Radio using real signals. Hello everyone, welcome back to GNU Radio. We'll start off by just picking up the audio from our microphones, and later we will connect an RSP to GNU Radio and see how to work with a real signal. So let's see how to add the microphone onto the GNU Radio canvas. We will search for audio source in the list of blocks and add it to the canvas. One thing you need to take into account is the sampling rate. This sampling rate now is dictated by the sound device, by the microphone, so it cannot be any value we choose. The default value is 32 kHz for the sampling rate of the script, but the microphone will likely be at another sampling rate. If we double click the audio source, we see that the sampling rate is a drop-down menu, and we can select between some different sampling rates. This must match the sampling rate of your microphone, and it's usually 44.1 kHz or 48 kHz. It depends on the microphone you're using and your sound device. We'll choose 48 kHz because this is the sampling rate of this microphone. But you can find your sampling rate on the settings of Windows, or you can choose any of the two. It will work anyway with only some slight stuttering. We'll choose 48 kHz and press apply and OK. And just to be safe, we'll also change the variable for the sampling rate, because now we have changed the value inside the block, but we haven't changed the variable itself. So we'll change the variable value to 48 kHz to match the sampling rate of the audio. Then we need some way to display this information. We'll use a Qt GUI sync, and you'll notice that the audio source is a float, it's a real signal, while the default for the Qt GUI sync is the complex signal. So we'll change the Qt GUI sync type to be float and press OK. We'll connect the two blocks. Keep in mind that we do not need a throttle block, because now the timing is dictated by the audio source, so we can connect them straight from the source to the sync. We'll press play, and you see there are no errors about the throttling, and you see that there is a signal in the FFT. This is actually a microphone, so you will see the audio displayed on the FFT, and if you actually go into the waterfall, we get some more interesting data about the audio. You can also see that since the signal is float, so it's a real signal, the imaginary part of the spectrum, the negative frequency part of the spectrum, is just the mirror image of the real part. So what is displayed here is the power of my voice in the frequency domain, and I can, for example, whistle, and you can see the peak of the whistle inside the waterfall. Same for the frequency domain in the FFT. The peak of the whistle is displayed in the FFT. This is because the whistle is almost pure sine wave, so it's displayed as a single frequency on the FFT. Let's say that we want that the whistle is something we want to know a little bit more about, so we want to be able to isolate the whistle between all the different frequencies, because now you see we have 24 kHz of range in audio, which is half of the sampling rate. But our whistle is around 1 kHz, so we have 23 kHz of unused bandwidth that we do not need. It might be useful to zoom in on the whistle. Of course, we can click and drag on the frequencies we want, and then the whistle will be zoomed in, but we lose quality. There is still 20 and something kilohertz of bandwidth that we do not need. So it would be a good idea to reduce the sampling rate, so to reduce the bandwidth, so that we only use 2 or 3 kilohertz or something like that. To do this, we can use a low-pass filter. What the low-pass filter does is suppress the bandwidth of signals of a frequency higher than the frequency we choose. Let's see it in action. Let's look for low-pass filter in the block selection. Let's change the type to float. So it takes float as an input and a float as an output. Let's connect it. And then we can choose two main parameters, the cutoff frequency and the transition width. The cutoff frequency is the frequency at which we want the attenuation to start. So if we choose 2 kHz, any frequency above 2 kHz will be attenuated. The transition width chooses how quickly the attenuations happen. So if we choose a big attenuation width in Hertz, then the transition between a non-attenuated signal and an attenuated signal will be wide. If you choose a slim transition width, then between the non-attenuated and the attenuated signal, part of the spectrum, it will be a very steep attenuation. The steeper the attenuation, the higher the CPU consumption. So we'll choose a transition width of around 1 kHz, 500 Hz. It's usually a good value. Let's choose 1 kHz and see what happens. Let's press OK and press play. You can see now that the spectrum used comes to around 2 kHz. And everything after 2 kHz is very, very quiet. The power, relative power is less than 120 dB. If you go to the waterfall, this is even clearer. You can see that now all the power is concentrated between 0 and 2.5 kHz, more or less, and anything after is very attenuated. So all the signals after 2.5 kHz are almost ignored in our signal. But still, this hasn't helped us a lot, because we still have 20 kHz of unused bandwidth. This bandwidth we don't need, and we still carry it around for no reason. So we can try to remove this part of the spectrum altogether. To do this, we use a function called decimation. The decimation is used to reduce the sampling rate of a signal, and in turn it reduces the bandwidth used by the signal. The decimation is available in a low-pass filter. You can see the first parameter is actually decimation, and the decimation chooses the coefficient by which the sampling rate is divided. Our sampling rate is 48 kHz, so we have 48 kHz of bandwidth, or in case of real signals 24 kHz of bandwidth, because the real part is only half the sampling rate. If we decimate by 2, we reduce the sampling rate by 2, which means that the sampling rate goes from 48 kHz to 24 kHz. If we decimate by 10, the sampling rate goes from 48 kHz to 4.8 kHz, so divided by 10. Let's choose, for example, a decimation of 10. And now we know that between the left of the low-pass filter and the right, the sampling rate is divided by 10. We need to take this into account when we tell the GUI sync what the sampling rate is, because now the GUI sync expects a sampling rate of 48 kHz. But we are feeding it a signal of sampling rate 48 divided by 10, so 4.8 kHz. So we'll open the GUI sync and tell it the sampling rate is divided by 10. In this way, it knows that the sampling rate is 4.8 kHz. Let's press play. And we see now that the bandwidth goes up to 2.4 kilohertz. And all the white space above 2 kilohertz, 2.4 kilohertz, is not wasted anymore. Now the whistle, you see, it is more clear. It is 1 kilohertz. And we could isolate it even more. This is something that is often done with real signals, because often when you receive from an SDR, you have something like 2 megahertz, 8 megahertz of bandwidth, but you do not want all that bandwidth because your signal occupies only a small part of the bandwidth. So you want to limit, you want to low pass filter the signal in order to remove frequencies that you do not want, and you want to reduce the sampling rate, both to reduce the CPU consumption, and you also want to remove from your signal all the frequency that you do not use. A good thing to do is, when you apply a decimation, is to create a variable object. So you will look for variable in the search menu and drag the variable object in the canvas. And the variable object has two parameters: the ID, which is the variable name, we can call this decimation, and a value. Let's give it the value that we gave it before, decimation of 10. Then we can substitute this variable inside the blocks that need to take into account the decimation. So we'll type decimation in the low pass filter, so it knows that the decimation is 10, and then the Qt GUI sync will tell it that the bandwidth is the sampling rate divided by the decimation. This means that now we can change the decimation at will, but just changing the variable, and all the parameters change as well at the same time. This is useful to avoid mistakes. If one changes the decimation at one point, you don't need to update the variable, the parameter, through all the other blocks, because it's done automatically. Now if you press play, you see the bandwidth is 9.6 kilohertz. For this next part, we plug in our RSP to the computer using the USB cable, and we'll put on a monopole antenna in order to be able to receive FM radio. Let's remove this old script and let's look for RSP. We have an RSP 1A, so we'll add an RSP 1A block. Depending on your RSP, you can choose any of the blocks available. And let's see what the parameters are. There are a lot of parameters to choose from. The sampling rate is the sampling rate of the RSP, which is usually you can choose a value between 2 MHz and 8 MHz. You can see the available sampling rates, for example, by opening SDR Uno, and you can see the sampling rates available are 2 MHz, 3 MHz, 4 MHz, up to 10 MHz. These are the sampling rates you can choose also on GnuRadio. To change the sampling rate, we need to change the variable, or we can type it directly in here. Let's change the variable and type 2 MHz. We can either type 2 million to choose 2 MHz, or we can also type 2E6. 2E6 is a common way to write 2 times 10 to the power of 6. 10 to the power of 6 is 1 million, which means 2 times 1 million, 2 MHz. And you see the variable changes to 2M, 2 MHz. Then the RF frequency. This is fixed by default at 10 MHz. We'll leave it at this for a moment. The bandwidth as well, we'll leave it to 1.5 MHz, which is compatible with the 2 MHz we chose. LO mode and IF type, we can leave this unchanged. These are more complex parameters that we can ignore for now. Automatic gain control, we leave this to true to allow the SDR to choose its own gain. Bias T, we will change the bias T depending if we have LNA connected or not. We discussed what the bias T is in previous lectures. And we can leave the other parameters as default. These are parameters that are available as well in SDR1. You have the IF attenuation, the intermediate frequency attenuation of the SDR, a linear attenuation step, the C offset mode, the notch filters, and the Q balance mode. These are all parameters also available in SDR1 that we leave untouched. To display the signal, we can connect again a Qt GUI sync, and we can connect them directly because they're both complex type. We press play. The signal is too powerful. To reduce the power, we can increase the LNA attenuation step, which reduces the power coming from the LNA. We can type, for example, something like 20 dB. Press play, and then we get the radio stations. This happens if the signal is too powerful, because it will overload the SDR. Now we see the signals. It would be nice to be able to change the frequency while executing the script. To do this, we can add a Qt GUI range, which we saw in the previous lecture. We can name the variable frequency as before, give it a label, and we'll note the fact that we will type the number in megahertz. Let's give it a default value of 100 megahertz, a minimum value of 90 megahertz, and a maximum value of 110 megahertz. The step could be something like 100 kilohertz. Let's then put the frequency variable inside the RF frequency of the RSP as frequency times 1 to 10 to the power of 6. So this will tell us, since the frequency variable is 100, to put it in hertz, we need to multiply it by 1 million. So 100 times 1 million, 100 megahertz. Let's press OK. Press play. And now we can change the frequency of the reception by changing the slider. Okay, let's say that we want to receive a particular station. For example, let's try to receive this station, which is at negative 400 kilohertz, so it will be around 99.6 megahertz. Okay. If we want to receive this station, one thing that we'll need to do is ignore all other stations, because now if we were to demodulate the signal, we would demodulate the FM station, we would also demodulate all the bandwidth around this FM radio station, because these signals are present and will be demodulated by an FM demodulator. So we need to attenuate all the frequencies which are not the FM station we want to receive. To do this, we can use the low-pass filter that we've used before. So let's look for low-pass filter. And let's also change the default frequency to 99.6, so that we do not need to change it afterwards. Let's put the low-pass filter in the middle. And let's give it a cutoff frequency of around half of the bandwidth of an FM radio station. The FM radio stations are around 192 kilohertz, so half of that would be around 100 kilohertz. Transition width, it does not need to be very steep. It could be something like 10 kilohertz. While we have the chance, we can also decimate the signal. Since we'll only be receiving a signal which is 200 kilohertz wide, more or less, we can decimate the signal by 10, so that the sampling rate goes from 2 megahertz to 200 kilohertz. Of course, we need to take this into account in the Qt GUI by dividing the bandwidth by 10. Let's press play. And now we see that the frequency goes from negative 100 kHz to plus 100 kHz, and only we get one radio station inside. At this moment, we could receive the radio station using an FM demodulator. If you look for modulators, there are several FM demodulators. What we want to use is the wideband FM receive, because we are trying to receive a wideband FM radio station. We could also use an FM demod block, but this is custom made to receive FM radio stations, so we'll use this block. This block will go after the low pass filter, after the signal has been decimated, and you see that the output, let's put it in parallel with the Qt GUI sync, and you can see that the output of the FM receive block is a real signal, it's a float signal. This is because the output is an audio signal, which we can play in our speakers. The wideband FM receive block takes in two parameters: the quadrature rate, which is the sampling rate of the signal in input to the receive block, and the audio decimation. Let's first put the quadrature rate, which will be 200 kHz, because the output of the low pass filter is 200 kHz. The audio decimation is the coefficient by which the quadrature rate is divided, and to dictate the sampling rate of the output. So if we type 1, we will get a sampling rate in the output of 200 kHz. If we type 2, we will get an output sampling rate of 100 kHz. For now, we can put a sampling rate of something like 4 or something like 4, because like this we will get a sampling rate in output of 50 kHz, which is more or less similar to our speaker's sampling rate, to our sound device sampling rate of 48 kHz. But if we were to pull, we can look now for an audio sync. The audio sync is our speakers, and we can choose the sampling rate from the drop-down menu. Of course, the sound device is still at 48 kHz, but we know that the output of the wideband receive module is 50 kHz, so there is a slight mismatch between the two. We could try to connect them anyway, but it would be better to resample the signal as such that the sampling rate incoming into the audio sync is exactly 48 kHz. Resampling a signal can be done with a rational resampler, and what it means is changing the sampling rate of a signal. We can, in theory, change the sampling rate of a signal to any other sampling rate using the rational resampler, which increases the sampling rate by the interpolation coefficient and reduces the sampling rate by the decimation coefficient. In total, the sampling rate of the signal will be multiplied by the interpolation and divided by the decimation. It's called a rational resampler because the end effect is to multiply the sampling rate by the ratio between the interpolation and the decimation coefficient. Let's open the properties and change the type to float, because it takes a float as an input and a float as an output. And since we need to transform a 50 kHz sampling rate to 48 kHz, we can divide by 50 and multiply by 48 the sampling rate. So we'll divide 50 kHz by 50, 1 kHz, and multiply it by 48, getting 48 kHz as an output. Let's connect the blocks, And in theory, if we press play, we should be able to hear the radio station. Okay, the audio is very loud. We can reduce the volume by adding a multiply constant block in between the rational resampler and the audio sync. The multiply constant block multiplies the signal by a constant. The constant could be, for example, 10 to the minus 3, 0.01, which reduces the signal by 1000. Let's press play. Okay, we can hear something, but it's very quiet now. We could think of adding a QT range. We can call it volume, starting at the default of low volume from 0 to 1 with a step of 1/1000, and we can put it here. Now we'll be able to change the volume by using this slider. Okay, we've successfully received an FM radio station using an RSP at GnuRadio. You can see now that GnuRadio offers great flexibility. You can do anything you want with your signal using the included blocks, or you can actually create your own blocks if you need. You can see that GnuRadio offers a great flexibility. You can play around with your signal, you can change sampling rate, you can apply filters, you can apply demodulating blocks, and this allows you to have a great control over the data, and it allows you to create simple applications to manipulate signals coming from an SDR. In our next lecture, we'll see how to receive a signal from a transmitter, and we'll see how to receive a signal from a digital transmitter, and how to manipulate and save data from a digital transmitter using an SDR at GnuRadio.
So that's all for the lecture and the video tutorial. The next video tutorial will be linked to lecture number 7 of the course, receiving data from a dummy transmitter. Thank you for watching this video. We hope that it's supporting teachers and students during the execution of the course. We remind that all the materials can be downloaded for free on the SDR Play website. The link is in the description of this video. Thanks for watching and see you soon.